Hi, everyone. My name is Ryan Fisher, and in this week one discussion, I'm going to go over a problem or two. Dr. Kerr was kind enough to allow us to use video, which I prefer. So I'm going to go to my MCAT practice prep and go over a problem that I actually originally got wrong. I like to focus on these, obviously, to get better. And I'm going to explain what I learned about this process. So the question says, which of the following reasons best explains why it is possible to separate a one-to-one mixture of one chlorobutane and one butanol by fractional distillation? So my original thought was, well, they're both polar. So that's probably why. And that was the wrong answer. And that led me down a path of learning about distillation. So I'm going to go to an image here. So distillation, to put it into simple terms, is the boiling of a solution, which creates vapor, and then we check the temperature of this vapor. So basically, to put it into very simple terms, because it is a little bit more complicated than this, but the temperature of the vapor is being checked at all times. And when we hit a steady temperature that matches close to our first boiling point of one of our solutions, and it's staying there, we know that is that we are vaporizing the very first chemical or compound. And then it'll go down this tube and it'll collect down here. Now, at some point, this temperature is going to start rising again. And what that tells us is that we are now starting to vaporize our second compound that was in our solution, because it needed a higher boiling point in order to get it from our aqueous phase to our gas phase. And that's how distillation works to separate. So if we go back to our problem here for a moment, we can see that we're separating chlorobutane and 1-butanol. Now, the key here is, for example, if you see chloro, we know there's a chlorine involved. And if you see OL, we know that there is an alcohol functional group involved. So how do we tell the difference between which is going to vaporize first and which will vaporize second? Well, the key is that the boiling point of 1-chlorobutane is lower than that of 1-butanol. And the reason for that goes back to even general chemistry. If you remember, hydrogen bonds are very strong bonds. And the alcohol group in the butanol, the OL, creates an opportunity for hydrogen bonds. And therefore, it'll take a higher temperature for it to boil off than it would for just the chlorobutane. So for that reason, the boiling point of 1-chlorobutane is lower than that of 1-butanol. And also for that reason, the chlorobutane will vaporize first, leaving just the butanol. And that is one way that we can separate two mixtures, and in this case, a one-to-one mixture. I hope you learned a little bit of something from this question. And if you have any questions about this problem, please feel free to leave them below, and I'll do my best to address them. Okay, here's another problem that I did, and one that I got right. And this one asks, which of the following oxidative transformations is unlikely to occur? And the right answer, ended up being a tertiary alcohol to a ketone. So for those who don't know, a ketone looks something like this. We have a carbon that is double bonded to an oxygen. The lone pairs are not shown. And that carbon is also bonded to some R groups. So if we go back here, as I said, the answer is a tertiary alcohol to a ketone. And the reason this is unlikely to occur is if we go to my sketch pad here, I have drawn this in more of a Lewis structure type of manner. And you'll see our carbon that is attached to our alcohol, and you'll see our three R groups. If this hydrogen were to be taken away or oxidized, then what we would like to happen to make a ketone is for this right here to turn into a double bond. And I'll cross out this hydrogen so it's not as confusing. And then we would still have our two lone pairs, and therefore we would have attached to its R groups. However, you can probably see the problem here. If we do this, then we have 2, 4, 6, 8, 10. Our octet is disturbed. So in other words, we can't do this. Instead, the best case scenario is this stays a single bond. We add another lone pair here, and this becomes a O minus. So if we go back to our question, which of the following oxidative transformations is unlikely to occur, the answer is clearly B, which is a tertiary alcohol to a ketone. Okay, and for my third contribution, this is another problem I got wrong, and it was a simple issue of Z versus E. I got the name right, just the Z and E wrong. You can see I picked E, and it's actually Z. So I'll teach you what I learned in getting this wrong. And obviously, if Dr. Kerr would like to add anything or correct me, please do feel free, of course. So when we are naming an organic compound, we want to go with the longest chain. So if we start up here, we go 1 carbon, 2 carbon, 3 carbon, 4 carbon. But then we got to double check the other way too. 1, 2, 3, 4, 5. So this way is actually the longest chain. So this is how we're going to name it. So to naming, the first one will be methyl, ethyl, propyl, butyl, and then pentyl. So you can see that the P, E, and T are an A and B. So we can cross out C and D right off the get-go. C and D are no longer going to be in our orbit. So if we take a look at where our groups are, we can see that if we go this way, this will be the first carbon, second carbon, third carbon. And if we go this way, first, second, third. So it doesn't matter which way we go. You want your group to be on the lowest carbon, but in this case, it doesn't actually matter. So it's going to be 3 because this is on the third carbon, which is a methyl. And this right here, double bond, makes it an alkene. So it's a 3-methyl pentene or 3-methyl pent-2ene. And then when we are figuring out Z versus E, this is what I learned when I was doing this problem, is you want to look at where your highest priority groups are. So if we split our double bond right down the middle, and if you have the highest priority group on each side, for example, each on top or each on bottom, then you have a Z configuration. If up or down is high or low, then it's going to be an E configuration. So if we go back to our problem here and we split this down the middle here, you can see that we have a methyl on this side, this carbon attached to 3 different hydrogens here. And on this side, we would have an ethyl. We would have a CH2 here and a CH3 here. So on both of our bottom sides, we have our highest priority groups. And if we go back to our image, when that happens, when we have our highest priority groups on both sides, this is a Z configuration. So I should have done Z3-methyl-pentuene, but I made a mistake and did E. So that is my other lesson for today. Again, if you have any questions, please do feel free to ask me. I'm learning just along with you and doing my best to kind of conquer these topics. So if anything I say is not perfect, please do feel free to correct me, and I would love to learn along with you.